Um, we already are seeing that the amount of chlorine in the troposphere, that's close down to the ground, has already passed its maximum. Its maximum concentrations of tropospheric CF chlorine provided by the freons, the CFC 11, 12, and 113 gases, that has maximized already around 1995, and we see this very slow decline in concentrations of chlorine in the stratosphere, in the troposphere. In the stratosphere it takes a little longer because it takes time before the CFC gases can be lifted in the atmosphere into stratospheric altitudes. So with regard to the stratosphere, we are now about at the time when we have reached maximum levels of chlorine in the stratosphere. So from now on, very slowly, we will return to more normal conditions. But from time to time, this recovery, which will take a long time, will be disturbed by very bad years when the temperatures in the stratosphere just stay at very low values. And that is unpredictable. That's dependent on the meteorology of in the stratosphere also, and you know how unpredictable weather can be. The effect of the agreements to phase out the CFC gases is very drastic. In the upper part of this curve, you see various curves. If no regulations had been issued on the production of CFC gases, if there were no protocol, Montreal Protocol, then the amount of chlorine would have been rising very rapidly in the atmosphere, reaching by the middle of the next century concentrations of the order of 20 parts per billion in the atmosphere, about 8 times larger than actually nowadays is found in the stratosphere. So it is very, very good that measures are taken. The initial measures was the so-called Montreal Protocol. In the Montreal Protocol, it was agreed upon to bring down the production of CFC gases by a factor of 2. But you still see that the amount of chlorine in the stratosphere kept rising because the emissions are, even on these amounts, are still larger than can be broken down by photochemical reactions in the stratosphere. Even the London Agreement, which was a further strengthening of the regulations, even that would have led to a further increase of ultraviolet radiation, of CFCs in the stratosphere and ultraviolet radiation. First, through further agreements in Montreal, we have reached a situation in which we gradually return to normal conditions. However, if you look at the lower part of this curve, it's about at that time when the ozone hole will have gone that we also have reached the largest effects on excess skin cancer cases in the atmosphere, because on top of the slow removal of the CFC gases from the stratosphere, the effects of the solar radiation on causing skin cancer in human beings is delayed. You don't get easily skin cancer when you're young, but when you are 60 or 70, that's the time when you are punished for lying in the sun and doing sun bathing when you were 20. So we have these long delay factors indicating that with regard to the effects of CFC gases on ozone, we haven't reached the maximum. Still further increases are expected. We see that we are now looking at various gases in the stratosphere. We already indicated some gases which are listed here. We see a slow return to normal conditions. In other cases, the amounts of gases increases with time. We have the scales, I hope you can read them. These gases which increase further in the atmosphere, these are the replacement products for the CFC gases. And they are adding something to ozone depletion, although by far not as badly as the CFC gases would have done. Finally, let me let me tell you something about a nightmare which I had, a scientific nightmare, not a real nightmare. And this concerns bromine. Bromine, on a molecule per molecule level, bromine is about 100 times more effective in destroying ozone than chlorine is. So one can ask the question, what would have happened if the chemical industry, instead of producing chlorine-containing halocarbons, had produced bromine-containing halocarbons? Or also, we can say it in other words, at the beginning of the 70s, when we started to discover when we were not yet aware of the danger of these gases in the atmosphere, we knew very little about their chemistry. For the same money, the chemistry of chlorine could have behaved the same as the chemistry of bromine. We didn't know that. If that would have been the case, we would have rushed into very dangerous situations already by the middle of the 1970s. Already by the middle of the 1970s, ozone would have been depleted everywhere, not only at high latitudes, but everywhere by a factor of 2 by the action of the bromine gases in the atmosphere. And that is because bromine, in comparison to the chlorine gases, bromine is, much of it is always available in this very aggressive form, in the form of Br atoms, BRO radicals, and molecules like HOBr. And they enter into catalytic destruction reactions, which are very rapid. So we are just very lucky that we never entered into a situation like that. But it was certainly not because we were so wise, or chemical industry, or we scientists were so wise. We're just very lucky that chlorine needed ice particles to become very active. If it had been bromine, they don't need the ice particles. They are largely in the activated form. So, what does this teach us? Well, we should also, in the future, we should very much stay, we should continue to be involved in research. For each molecule, or each compound which are put into the atmosphere, also in waters, let us be very careful at looking what are the consequences. The ozone hole was totally unpredicted. Our science was not good enough. Our science is maybe never good enough, but we should at least try always to be able to predict some of the worst consequences. Another thing we have learned is that things were actually much worse than we initially believed. Roland and Molina predicted ozone depletion above 30 kilometers. But the very large ozone depletions which took place at lower altitudes, they were not predicted. They were measured first. We saw the ozone hole and needed an explanation. And that means that we must continue making measurements, because our theories may never be really enough developed to be sure that we make the right predictions. And of course, a very important lesson is that we have seen that a part of the atmosphere, in a chemical sense, became unstable. We had a runaway effect developed at high latitudes in the northern, to some extent in the southern hemisphere. And if you look at if you consider another issue, and that is of global warming, by the increase of carbon dioxide in the atmosphere, chemically and physically and biologically, a much more complex issue, then you ask yourself, is it possible that this climate regime, or parts of it, will enter under very unstable conditions? I'm saying this, there are some examples of things which might happen. We cannot prove it, but we should occasionally look for worst case situations. And here I would like to finish, and I hope for a vivid discussion. Very nice talking to you. Thank you.
Can you put on the light, please? I would like to open the floor for questions and discussion. And please introduce yourself before asking the questions. And I would request it to be very brief and to the point so that we have more people from the floor can get a chance to discuss their point of issues. Yes.
Professor, I'm really feeling myself very fortunate that I could listen to your talk. My name is Sadananda. I'm a professor of computer science. I am not a chemist. My knowledge about chemistry is very meager. I just would like to ask you, although you mentioned about the Antarctic area's ozone depletion and also mentioned the Arctic area, but most of the attention is only on the Antarctic region. Most of the human actions are in the northern hemisphere, isn't it? Why is it that there is not so much talk about the Arctic ocean, except one slide I saw where you mentioned about it? And I would be curious to know about it. Thank you.
So if I understand correctly, your question is, why is especially Antarctic so much affected by human activities?
Not the other side. There is no human.
Yeah. Well, this had to do with, it doesn't really matter anymore. If you have gases with very long lifetimes in the atmosphere, they get by transport in the atmosphere by winds and by turbulence, they get everywhere. So you have about as much CFC gases in the northern hemisphere as in the southern hemisphere, as in the tropics. There's not much difference. The same is true for the stratosphere. So that the action of the CFC gases is the concentration, so to say, at various altitudes is about the same. And then if there are special conditions arising in the stratosphere over Antarctic, like low temperatures and sunlight, if these conditions are fulfilled, together with the chlorine, which is transported everywhere, then you run into these very unstable chemical conditions, in which during a period of about 3 weeks, a maximum in ozone concentrations, just there exactly, is converted into a minimum, into the ozone hole situation, between 12 and 22 kilometers altitude.
Hello? Please switch on the microphone.
Thank you, Dr. Crutzen. In the introduction, they mentioned that you were studying the effects of high-altitude aircraft. Could you share some of your findings with us about that? And the other question that I have, my understanding is that ultraviolet radiation produces ozone. So as it increases the CO2, doesn't it also increase the ozone itself, especially where the hole would open and the radiation would penetrate deeper into the atmosphere? Wouldn't that create more ozone?
Yeah, those are good questions. To some extent you do that, but the effect is very small. By reducing ozone, indeed, ultraviolet radiation is coming down, further downwards into the atmosphere. However, ozone is formed by the photolysis of oxygen, of O2, at short wavelength, very short wavelength, below 240 nanometers. So, while the ozone destruction reactions are formed by ultraviolet radiation up to much higher wavelength. And that means that the ozone depletion reactions also are increased, and actually more than the increase in production of ozone. So these factors are overriding each other with the longer wavelengths finally taking over and causing more ozone depletion. That's one of your, does that, high-flying aircraft? Yeah. There I have to tell you something about the very complex role of nitric oxide in the atmosphere. You probably are very well aware that nitrogen oxides at low altitudes near the ground, together with the emissions of hydrocarbons and together with sunlight, produces ozone by photochemical smoke reactions. In the stratosphere, this is also the case up to altitudes of about 20, 25 kilometers. Above that, ozone is being depleted by the catalytic chain of reactions, second or third view graph which I showed you. So it's a question of where the aircraft flies. If they fly below 20 kilometers, they tend to make more ozone, basically by the photochemical smoke reactions. If they fly at higher altitudes, then they destroy ozone. Now, the aircraft which have been flying at lower altitudes than 20 kilometers. So we have never seen an ozone depletion. We have seen a small, we have even seen, our models show a small ozone increase in the stratosphere. In reality, this has, however, never happened because the only supersonic aircraft which would fly at high altitudes, they are no longer in business. The Concorde has been withdrawn from operation.
Yes, any more questions?
Professor Crutzen, my name is Chongnak Professor from Thailand. I am a water engineer. I like to thank you very much for the excellent presentation, and you give us some optimistic hope that in the next 40, 50 years, perhaps the ozone layer will be better. But this week or recent months, we have heard about some discussion about the Kyoto Protocol, which you did not mention anything about Kyoto Protocol. And there are some superpower nations that show no interest or no commitment to follow the Kyoto Protocol. If that is the case, what are your prediction or estimate? Would that have effect on ozone layer? I mean, greenhouse gases. Can you say a few words on this matter? Thank you.
Yeah, I cannot give you exact numbers, but the effect of increasing carbon dioxide in the atmosphere has the secondary effect that the lower stratosphere from about 17 kilometers upwards will cool and increase and promote the formation of ice particles. And ice particles, as I showed, are very dangerous if there's enough chlorine, if too much chlorine in the stratosphere. So the recovery of ozone may be further delayed. In some estimates, actually, we might have to wait on the end of this century. We cannot give a definitive answer. It depends on some properties of these particles and very much also on how much carbon dioxide is added to the stratosphere the rest of this century. It's the two countries, by the way, which are not signing the protocol of Kyoto. Those are the only two superpowers still having nuclear weapons in an oversupply. They're not behaving as they should.
Yes, any more questions? Yes, please.
Yes, could you address the other chlorines, other than just CFCs? Aren't the other chlorines also dangerous?
Yes, and the main compounds we have to worry about were the CFCs, but also carbon tetrachloride, methyl chloride, but that is largely natural, not totally, because it's also produced by biomass burning. And we have a number of other chlorine-containing compounds like C2, F2, F2Cl4, and etc. There's a whole battery of gases which were emitted in the atmosphere, but in lesser amounts than the CFCs. But the consequences are very similar. But what I showed you is really an addition not only of the CFC 11 and 12, but also the other chlorine-containing gases.
The chlorine we're using for water purification, swimming pools, and all of that.
Yeah, well, those chlorine gases which are produced that way, they are not in, except maybe chloroform. They are not. They're not in organic form. They're mostly in inorganic forms. They are removed from the atmosphere much more effectively by rainfall, by being taken up in cloud particles and then being removed by precipitation processes.
Thank you.
Thank you very much for your very interesting presentation. I'm Lette Mieke Mulder and I'm here this week to participate in a workshop on sustainability. And there we also address some of the more, let's say, softer sides of science. And what we can learn from the experience on ozone is, well, first of all, that there is a gap between there are scientific findings and facts and the time that actually there is some political and other action. And on ozone we were probably lucky because there were some clear things we could do. On some of the other issues, and I'm thinking in particular about global warming, the actions are perhaps, or the issue is perhaps much more complex. And I wondered whether you would have some recommendations and perhaps learnings based on your ozone experience that you could give to, let's say, the non-scientific community.
Well, you ask a very important question which is very difficult to answer, because basically we know what has to be done to improve the things in the climate warming issue. We know what has to be done. But the fight is about whether it will harm economies of some nations or not. And some nations just say that they're not going to take to follow the Kyoto Protocol because they think it harms their industry, their economic output. Other nations are of a different opinion. In Europe, we are a little better, not much better, because we are only reducing the emissions of carbon dioxide in the atmosphere compared to 1990. In the year 2012 by only 5 or maybe 8%. It's still peanuts. In order to stabilize CO2 in the atmosphere, you have to reduce the total emissions of carbon dioxide into the atmosphere by at least 60%. And if you want to reach such conditions, then you see the monumentous task we have ahead to get into this situation. And think, in reality, this cannot be achieved. We have unfortunately to live with the prediction that carbon dioxide will continue to grow in the atmosphere. But we should try to limit the growth as much as possible to prevent the worst things from happening. I cannot say much more than that. Some governments listen to us and me. Other governments just don't do that. But things will change. You can be an optimist, you can be a pessimist. Sometimes I have the feeling nothing will happen before some climate hole, we can call it, situation. Instead of an ozone hole, an instability in the climate system will develop. When that does, then maybe there will be quick action. But like was the case for the CFCs. But there is no easy solution, and we should continue to put pressure on governments, but everybody of us also singularly should do whatever he or she can to alleviate the problem. If you look at the development, the many cars around the world, now Asia is filling its roads with so-called environmentally friendly German cars. And you see the crazy situation. It's good for the economy of Germany, maybe, but not for the world. So the attitude, political attitude, has to change. I cannot really answer your good question.
Yes, any more question? Yes, please.
This is regarding your last slide. My name is Rakshit from AIT, Bioprocess Technology. My understanding is that in the chemistry labs, we normally handle bromine compounds much more carefully than chlorine. So you were suggesting that it was a bit of a luck, but what I'm trying to get out from you is that it's more because people don't use it because of its high corrosive nature. Is that true, or was it luck all the way?
Well, the chemical properties of the chlorine-containing compounds were more friendly than of the bromine-containing compounds. That's why the industry went into production of the chlorine-containing compounds. But then you can turn the story around. We didn't know anything about the chemistry, or not much about the chemistry of chlorine in the atmosphere. And by the same token, chlorine chemistry might have behaved as bromine chemistry. We didn't know from the beginning. If that had been the case, then we would have had catastrophic developments already by the middle of the 70s, when we did not have the instrumentation available to measure these highly reactive compounds in the stratosphere. And the theories had not been developed. With environmentally friendly cars, especially German cars.
Well, I think we have more opportunity to discuss with him informally after we conclude this session and have a reception in the dining hall. So at this point in time, I would like to invite our Register, Professor Gautam to give a vote of thanks.
The votes of thanks can be very brief. We can simply say thank you, Professor Paul Crutzen. But I shall take a little opportunity here to express my feeling after listening to his lecture. I didn't capture much the beginning of the lecture because it seems to be quite technical, but I think I captured the later part when you talk about how lucky we were, for instance, not to have used bromide, but also to have a scientist like yourself to help predict the effect of those CFC, and also lucky that we have successful protocol, maybe because the non-production of CFC did not affect much of the world economy, but anyhow we were so lucky. But on the other hand, I felt somehow unlucky when you said that it needs at least 40 more years, and when you say that 10,000 or 100,000 blind per 1% increase of the or loss of the ozone or whatever, and many more cancers are to be predicted. And with this, the cause and effects are not immediate. It takes so many years, and it should bring us more caution in our own behavior. But most importantly, I think Professor Crutzen has shown us a model of human striving for a better understanding of our environment. And also, as a scientist, he has shown that scientific endeavor is together with social responsibility. It is a scientific responsibility to give facts, a very well researched analysis, and warning to decision makers that what they are doing may have a very catastrophic effects if we are not be enough cautious in our work. And I think AIT is an institution where we always say that our mission is to develop highly qualified and competent professionals for sustainable development of the region. And then I think all of us should follow the example of our guest speaker today. I would like to thank all of you and would like to invite all of you to express our great appreciation to Professor Paul Crutzen. Thank you very much. May I invite Professor Mario Tabucadon to give a plaque of appreciation to our speaker. And I would like to announce that today is a very special day for Professor Paul Crutzen. If I'm not mistaken, he's exactly 70 years old today. So, as a token of appreciation, we have some little thing to show you now.
It's a pleasure that Professor Crutzen is celebrating his birthday with all of us. Let's wish him a very, very happy birthday. Happy birthday to you. All of you are invited to a piece of this cake in the dining hall now. No, dining hall. So please join us at the dining hall for a cake, tea and coffee.
It's here.
The CD, no?